Okay, we're here. Rubber hits the road, or pen meets paper, or chalk meets the board, whatever you can call it. We're going to start doing some problems. Now, for this video, I have 4 problems that I'm going to discuss and go over with you. What I'm going to attempt to do is solve them like I think an ideal examination response should be, and then I might do a little debrief, but I also will urge you to look at the time I take to solve it. And you ideally you got to do better than the time I do, and that will come with practice. So needless to say, for solving 4 problems in no way will keep you ready for any examination. You probably have to do about 100 times that, right, in order to develop that accuracy and that speed. But I'll try and explain what I do, and I'll try and make it as explanatory as I solve it. In your exam, you don't have to do that explaining. You just need to work the solution out. Right here, on the top of the of the screen real estate, I'm going to then add the problems that I solve, so you can actually look at it as I'm working on it. For my own sake, I have this piece of paper. Okay, so we'll get into it, right? And let's start with the first problem of the day. So you'll see that appear here, right? And here's how we're going to do this. So the problem, let's say, for all my problems, what I normally do is I'd say, what's given? You have the train whose mass m is equal to the engine, which is 5,000 kg, plus the carriage. You don't need to write this out in this form as long as you have your numbers captured accurately, right? So that the mass is 15,000 kgs. What else is given? We are told that velocity is v meters per second, and its constant velocity, which means acceleration, is 0. Okay, and we're also given the angle theta such that sine of theta is equal to 1 over 50. Additionally, we are given, and this is what is given. Let me just write m again here. Rate of work. And rate of work is simply equal to power, which is equal to 40 kilowatts, which is nothing but 40,000 watts. What else are we given? We're also given the force of resistance to motion, right? And this is non-gravitational of 2,500 newtons. What are we going to do with this? We're going to try and find the value of V. So what we will do first is go back to our concept of a free body diagram. So we will write a slightly exaggerated picture here. Show the train pulls it upwards, right? So it's pulling it up. So the train is moving in this direction. So that's the direction of motion. I have that clear. What happens to this? It obviously has a mass. So we're going to draw that line down here. This is the mass of the train, m, times acceleration due to gravity. Almost always, this is going to be 9.8 meters per second square, so that is fine. What are the forces acting? We have the resistance force. That's given. That's the vector for that. And what else are we given? We also know that mg gets resolved here in this angle. And if you know your trigonometry, if this is angled at 6 degrees, what would that be? That would be the sine of, so this is mg sine theta. Now watch that. All of that is given to you, right? The velocity is constant means there is a force of the, let me just call it engine. So in this particular problem, and in similar problems, this is called the driving force or the traction force or the tractive force. These are terms that you see in the Cambridge textbooks. Some of them call it the traction force or the tractive force. There are the curricula which call it the driving force. I'm just going to denote it as Fe. Now, for velocity being constant, that means acceleration is zero. There is no net force. The forces cancel out, right? Newton's first law, right? All forces cancel out moving at constant velocity. Now, what do we do here? We know Fr, we can calculate mg and sine theta, all of that's given to us. How would we work Fe, the force of the engine, right? We're given power, so we know power equal to force times velocity, right? At a given velocity, v, we can estimate this force times that velocity should give us power. Would that work? I think that makes sense. So our first equation here would be the force from the engine, right? And I'm going to do this. The magnitude of this force would be equal to the magnitude of mg sine theta, because it is a vector plus, and the reason why I'm doing magnitude, if you didn't have magnitude, you'd have to write this as the negative because it's in the opposite direction. The problem does not ask us about direction quite yet, so we're not worried about it, times the magnitude of the resistance force. Do we have all of this information? We do, right? So that's our first equation, and we could just say this is equal to mg sine theta, and I'll write it out for you. That would be 15,000 times 9.8 times 1 over 15. They made it really easy by giving you sine theta times, or rather plus 2,500 newtons. Okay? Again, all of this part you don't necessarily have to write in such detail on an exam response. You could go to this free body diagram. You could put this as your notes on the side, and then you go to this free body diagram and go straight here, right? So I will cut short some time, or rather save myself some time, and try and resolve an answer, get an answer for you here. And I think I have a cheat sheet. Yeah, there we go. Right? And here I have forces this. So how would I write this force magnitude here? I would then say the force of the engine would be equal to the power divided by velocity, right? Which then, if I brought it here, I could now, and that's equal to, let's make this a little easier, 40,000 divided by V, right? So if I had 1 and 2 equating coming back here, I would have 40,000 by velocity is equal to, and if I just simplified this, what would I get? 50, that would be by 5, 300 times 9.8 shy of, and that'd be 2940 plus 2500. Now, if I did the math there, what would I get? If these terms went the other way, velocity is equal to, what would it be? 40,000 divided by 5,440, and I would write my final answer. Velocity is equal to 7.35 meters per second in the box. That's the answer. So if you have this kept aside, if you've demonstrated this picture, if you've written out this equation, you've written out this equation, you've equated them, that means conceptually you've understood what's going on. Even if your calculation had a small error, they should give you part of the marks come through for that. I typically encourage you to put in your answers at least with 2 decimal points. Sometimes the question will specify how many significant figures that you need for that particular question, but that's entirely up to you, right? It's in the question, but don't try to leave it as 7 or round it to 8, and that's going too far. This is more like 7.53523, something like that. And I've just rounded to 7.35. This should put you in a good space if you've got these equations. Okay, so that completes the first question I wanted to discuss. We'll move to question number 2. Welcome to question 2. So here, let's see. This is an interesting one. I particularly like this. I'm going to go right all the way to this corner and say, given mass m is equal to 0.2 kg. If they gave it to you as 200 grams, make sure you fix it. And it's traveling with initial velocity u. You may want to, you don't have to write initial velocity. You could use the word u, it's fine. And that's provided to you as a vector, which is 5I minus 2j, right? And then, of course, they do this and give you meters per second. Now, they've also given you final velocity, which is 8I plus 4j meters per second. They ask you to find impulse. Now, this is interesting. The magnitude of the impulse and the angle of the impulse with I. So what I'm going to just do here is, for the sake of clarity, I'm going to do this. Again, you don't necessarily have to do this, but if you can illustrate something like this, it would really help, because the examiner then knows your concepts are very, very clear. So 5 and 2, I'm gonna, if I just go 1, 2, 3, 4, 5, and 1 and 2, I could just make a spot here and say that's my initial velocity vector u, right? And 8 and 5, 1, 2, 3, 5, 6, 7, 8, 1, 2, 3, 4. So somewhere here is my final velocity v. Now, we know impulse and impulse momentum. So they've said it's impulse. We know impulse. And I'm going to start doing this. Let me do it here, and I'll show you what is probably the most common mistake a lot of people make, right? Because the first part of the problem, find the magnitude of the impulse. You're going to say impulse is equal to final momentum minus initial momentum. And wait, the question saying magnitude, it's super easy now to say, oh, I just need the magnitude. I'll find the magnitude of u and magnitude of v. Mass is common, so I'm going to write 0.2 times. And the magnitude of v is 8 square, is the square root of 8 square, and 8 square plus 4 square, right? Minus the magnitude of u is 5 square minus, or rather plus, negative 2 squared. So that would be negative 2 squared. And I would go and say 0.2 and then bring out the calculator to do root of 80, plus root of 29. If you're going in this direction, this is wrong. And that is why it's important to stop, read the whole question. The whole question is talking about, hey, I also need to find the angle of the impulse with respect to I. This is I, and this is J, which means right away it tells you, if you looked at it, you're dealing with vectors, right? And when you're dealing with vectors, unless they're both in the same direction, you just don't add their magnitudes. Clearly the directions are different. I mean, if we resolved them, yes, we could add their magnitudes, but no, this was the initial vector. This is the resulting vector. So something else happened that has caused it. We could now, here's how I would approach it. I would put in another vector here called P is equal to AI plus BJ. That is the vector. And the math I would do, and here's how I would start off this problem. Let me take this off. Here's how my approach to doing this problem would be. Vector P vector is equal to momentum vector, right? Final minus momentum vector initial. I would now go in here and say AI plus BJ is equal to mass times the velocity vector, 0.2 times the velocity vector, final velocity vector, 8I plus 2J, subtract 0.2 times this vector here, which is 5I minus 2J, which I would then write as, I can remember a scalar quantity multiplying the vector. Both components of its direction are equally affected, right? Now, just for the sake of my calculation, I'm going to make this easy. 0.2 is 1 by 5. I don't want to waste a lot of time trying to do the math. I mean, these numbers are fairly easy, but I don't want to try and work decimals out. I encourage you not to as well. So this would simply, 0.2 to me is just 1 by 5. So I'm going to write this as 8 by 5 I, right, plus 2 by 5 j minus, this would become 5 over 5 I minus 2 over 5 j, right? Here, subtraction of vectors is basically the addition of the inverse of the vector, which means a 5 and minus 2 is a minus 5 and a plus 2, really, right? You can add those two vectors there, right? And if you go back to our video on vectors, you know it's just placing this vector this way and adding it, right? You can work that out in your mind, but for the back to solving this for the exam, that's how it would look like, which would now be written as 8 by 5, okay, adding the inverse, negative 5, which is really just minus 5 by 5 I plus, it's the addition of the two vectors, so that's what I'm going to do. What did I do here? I did something wrong. That's 4. That's 4. If this was an exam. 4 by 5. Now, this is a negative 2. I'm adding the inverse, so I'm adding negative of negative, positive 2. Remember this. If you know your vector as well, if I wake you up in the middle of your sleep, in the middle of the night, you should know this. Important. Okay, so that's how it is. So I'm going to write my P equal to, this vector is now written as, what is that? Fairly easy. I think it's 3 by 5 I plus 6 by 5 j. So I've got my a plus b for this vector. Now let's find the magnitude. Then magnitude of vector p is equal to, let's do this, square root of 3 square by 5 square plus 6 square by 5 square. Okay? Which is equal to, I can now write this, and again, I encourage you to, unless you've practiced a lot, I encourage you to do this. 3 square by 5 square. I've got my 5 square out, it's common. 3 square can come out because I'll have 2 square here, times 1 plus 2 square. These two come out, and I can write magnitude of P, magnitude of impulse is equal to 3 by 5 4 plus 1 root 5. A lot easier to represent this. And I believe this should be sufficient. However, I would also encourage that if you've got a calculator in the exam, you can quickly calculate a value for this and write it with 2 decimals as well, right? Magnitude of impulse. What would you write? Is this sufficient? No, this is not, because I am missing the units, right? Impulse is force and time, Newton seconds. sorry, Newton's second force times time. That's the magnitude. Now he's asking you to find the angle between P and I, which is this angle. If you know your math, it's easy, but otherwise you could basically say 3 by 5 I. So here I'm going to do this. If this is 3 by 5 and this is 6 by 5 and this is nothing but 3 root 5 over 5, you need to determine this angle. Angle theta is equal to, and here you can do sine, you can do tangent, you can pick one of them, use your calculator and do the trigonometry. You can just work this out. I might just do so tangent of theta. So I will do theta is equal to, so tangent of theta will be opposite by adjacent, which is 6 by 5 by 3 by, which is, and 3 by 5, right? So it's the inverse tangent of this ratio. So tan theta is this ratio, the inverse of this ratio, 6 by 5 divided by 3 by 5. If you work the math, again, this is nothing but inverse tangent of 2. You should be able to get your answer. And I think this would be about 63.5 degrees or to that effect, right? If you have this much written, revalidate, make sure your calculations are right. You've shown the person grading the exam that you understand the vector addition here. You also understand the impulse momentum principle, vector addition. You know what the magnitude now is. Clearly very different from if you did the previous incorrect method, but that's why vectors are important. And if you put this in there, they also know that, hey, you know what AI and BJ are, and this should, and I believe this calculation is accurate, but you're welcome to, if you've got all of this and you can do your calculation accurately, you've done this problem very well. But again, this is a classic A-level problem. It looks very simple. It's a very small problem, but remember, they're really testing you on multiple things. First of all, do you know how to manipulate vectors? That's there. More importantly, do you understand conceptually that these are vector quantities and they don't just get treated like taking the magnitude of these and then trying to calculate the magnitude of your, it doesn't happen that way because they have different directions. And the directional change happens because you've got another direction introduced here. So just going straight to magnitude would have led you along the wrong path. So this is a very interesting problem. I think this would be really useful. So that ends problem number 2. Problem number 3. So there we have it. And let's do the same thing that we always did. Let's see what we're given, right? We're given that a ball is dropped. What is given is the mass. We know that's 2.5. Oh, they're still nice. They give you the kilograms. And we know height. Now, you could write this as S or H. I'll just use H. If you remember that example where we did the vertical drop, we used H. Again, read the question thoroughly, and you'll see right away something to do with work. Work. So immediately I go back to that area where you did the energy work, potential energy, kinetic energy. So I like that H there. I'm not using S, and that's 12 meters as given in the problem. Okay. What does it say? Might also do a simple drawing here just to help me understand what's going on, right? So that's my H, right? And over here, my initial velocity would be 0 because I'm the ball gets dropped from there. Here, my final velocity, just at that point of impact, if you remember our lesson, is 10 meters per second. I like these diagrams because they're really useful. What's going on here? And they're telling you that there is the object is falling. So I'm going to draw my object here, right? And I'm going to show, and I'm going to call this F gravity. That's m times g. Remember, unless specified, acceleration due to gravity is always 9.8 meters per second. There is air resistance that is this way, and they've given that to be r. And that is, have they provided r? They haven't. They just told you there is an r. Okay. Now, as soon as we go a free body like this, we know that if this body is falling, it's obviously there's force, right? There's some kind of a force that's acting on it that's causing its velocity to go from 0 to this. So that immediately, intuitively should tell you that gravitational force should be higher than the resistance force. But the problem is now saying, what is the work done by air resistance? So if you're tempted to go and try and say S is equal to UT, plus half AT square and all of that, if you're tempted to go in that direction, just watch out. This is a work problem. And we discussed that if I move this up, I've increased potential energy, I'm dropping it. There is no mention of potential energy, but given final velocity, I can, in free fall, I can always say that, hey, there is that kinetic energy that changed from 0 to now I've been given this. So I will approach this problem starting with energy, and I would say kinetic energy, and I might even write this down for the examiner. Kinetic energy, I think I should get rid of this chalk and let me something else, is equal to 1/2 mass times velocity squared. So I know that. I've started with that. Okay. And I know that total work done is equal to the change in energy, change in kinetic energy, in this case, is equal to 1/2 mv squared, because that's all that happened, right? So I know that. So that's another part I've demonstrated. Now, total work done, right, which is also means work done by, so I will just say, so there's work done by the net force, right? So if I know the work done here, I know the net force here, right? So I'm going to now say this is equal to, let me just say this is 1/2 times 2.5 times 10 squared. Okay. You can kind of work a value out, which is basically 2.5 or 1.25 times 100, which will give you 125 for work done, which is basically force times distance. So it's Newton meters, which is also sometimes stated as watts. No, joules. Right? So that we know. Now, here's the second one, net force. So I'm going to say net force is equal to, so force of gravity minus R. Right? So I'm going to call this F net. Force of gravity is 2.5 times 9.8 minus R. What do I now have to work out? I don't know Fnet, but I know work done is basically force times distance. So I can come back here and say, if that distance is 12 meters and the net force acting has been whatever newtons, force times distance will be equal to that, Newton meters. So I'm going to equate this, and here I can actually say this is nothing but net force times h as the distance. So that would be one equation, and that would be another equation, which I can then equate and write as, think about it this way, 1/2 times 2.5 times 100 is equal to 2.5 times 9.8 minus R. So I've gotten that. Now, why am I working through all of this, right? You could take an alternate approach, look at the first part of the problem and say, oh, I just need the net work done. I can calculate work done by FG, which, calculate the number of joules that you get out of it. I can go in here and say, this is the net work, subtract the joules and come up with an answer for R. Yes, that works too. But I'm going to find R because the second part of my problem anyway tells me to find the magnitude of R. So we're a lot happier just finding the magnitude of R here, right? And again, these are forces, so I should be saying magnitudes, and this is magnitude, in which case my magnitude of R is equal to, so if I do the math, let's see what that works out to. 2.5, and that works out, I think that's approximately 72.5 newtons, right? So that's how the math adds out. I don't encourage you to skip the steps, do the math. So that's one way of approaching this problem. I'm going to do another, and then you can take this, multiply this by 12, and you can say work done by R is equal to times H, and your answer then would be that times 12, and you basically get an answer. Actually, you know what? I might be mistaken. This is not 72.5. This is 14.08 newtons, and 14.08 times 12 gives you 169. Don't forget the units, joules, right? So that's how you'd get these, right? So one method of solving it. I'll stay on the same part, give you another method of solving it. So that's total work done, 1/2 in joules, and I'm going to say by Fg is equal to mgh, and that's equal to 2.5 times 9.8 times 12, and I can now say work by R is equal to total work done minus work by Fg, and I can now go into this one, do the math here, and I would get something to the tune of work done by gravity. Yeah, total work should give me the same. Did I get it right? That's the total work done. Should be adding this, I believe. See, that's the mistake here because of directions. These are vectors. My mistake, right? So in this particular case, because of directions, total work is equal to work by Fg minus by R. Now, if you didn't put this there, first of all, it would be very misleading. But the idea here is because I have directions, I stated it this way. Your examiner may be tempted to look at this and say, do you understand directions? Because in any other form, you would have ended up with a negative value. And that is important because they're not asking you for that vector. They just want the value of the work done by air. So now if I flip this around, now I can say you see, if I move this work done by gravity, I'd say 2.5 times 9.8 times 12 minus 1/2 2.5 times 10 squared. Do the math, you should get 169 joules, right? And now to find magnitude of R, I would just say magnitude of R is equal to work by distance. Again, it's magnitude. So if you did have a negative value in the previous case, if you had a negative value and you found negative value coming here, magnitude takes that negative value out. So you'd still be okay, right? And looking at the problem, he doesn't actually ask you for, yeah, he's just basically saying work. So you could technically have a negative value, but that would be wrong because it's incorrect. There's really not negative work in this particular case. But remember, with this diagram, you should have this fundamental understanding. If you choose this option to work the problem, that would be 169 divided by 12, and that should give you 14.8 newtons, or 14.08 newtons, I think that is 0.08 newtons on your calculator. That should give you the same answer, but another method of doing it, right? So two approaches, one just following the problem itself, the other finding R. And I prefer the first method because exactly for the same reason. If you don't naturally just intuit this work equation, you might be tempted to just add them or put them in the wrong order, and then everything messes up. But if you can just get it, then you're good, right? So that's that part. Now he says, I've modeled air resistance R. Now I've done this, where the magnitude of R is provided by, is equal to 10 plus 2 times velocity square newtons. Find the maximum possible velocity of the ball in the new model. A maximum possible velocity means acceleration is 0, which means there are no more forces acting on it. So sum total of all forces becomes 0. If you did that, what does it mean? It simply means if V is a constant, A is 0, implies force of gravity magnitude is equal to magnitude of r. I think we can work the math out now, which means force due to gravity m times g is equal to magnitude of this is given by 10 plus 2 times v squared. So moving this around, again, I encourage you to not skip steps. Just 2.5 times 9.8. That's the m times g. 10 is subtracted out of it, divided by the 2v squared, so the 2 comes down here. So if I do that, and I've done my math right, is my math correct? I hope it is. Oh no, it's modeled as 0.2. Look at that. I didn't capture that. Looks like I need new glasses, which would be 0.2. Yeah? Velocity square would be equal to 72.5, and therefore V is equal to 8.52 meters per second. In the new model, the ball would race from 0 to that velocity, and it stays there because that force due to that force driven by gravity is balanced out at some point by the resistive force, and that's typically called terminal velocity. But here you go. This is a rather simple solution to the problem. Don't make the mistakes I made, which is reading the question incorrectly. Read it carefully. I should too, but this is really small print as I've crammed a lot of things. But that ends. So before end, so temptations. You might look at this and start saying S is equal to ut plus half at square, or you might be tempted to say v square is equal to 2gh, things like that. Avoid the temptation of that. This is a work problem. When you see work, work done effectively is a change of energy. And in free fall, in this special case, we could actually write it this way. And if you had that idea, that's what they're looking at. And if you can relate work as a force times distance, then you are generally fine. If you also wrote work in this form, they know that you understand how they cancel out. Your examiner should be pretty happy with this answer, and you should be able to get. I think a problem like this is, you've got 1, 2, and 3. Probably get you, graded in 3 different ways, maybe 3 marks each, and this might be 2, or this might be 3, and those might be 2 each. So that ends problem 3. I will see you on problem 4. Welcome to problem 4. So this is an interesting one. This is a classic A-level type problem, and let's see what they're asking you. So they're asking a fair bit. This has got 3 parts to it, but we will do the same things that we've always done, which is let's take a look and let's work this out one part at a time, because they've clearly split out this. They've given you a model, they ask you to find acceleration, then they change it to downhill. So there's fundamentally, so we'll do this in parts, and we'll try and work through this. This is an A-level problem, and I can tell because it says show that the driver will need to brake to maintain speed. So it's not saying calculate a value. You're going to arrive at a result that is, you will support that result numerically through the math. But here the expectation is that you can comment on that result. Okay, this is going to be interesting. Let's now take this problem and say what's given. We are given the mass. We know mass. Again, put it in the same place. 1,400 kilograms. And we know this initially is horizontal road, and he says speed. Well, they're actually calling it speed. It's called V meters per second. He's added friction and everything else and says your resistive force of resistance, the magnitude of which is provided by 120. I better be careful this time. Plus 2 times V square newtons. Don't forget the newtons. And he has provided the engine of the car is working at a constant rate of work. I always like that. Basically, power is equal to 20 kilowatts. I'm going to write that as 20,000 watts. Okay. Find the acceleration of the car at the instant when we. This is a very, again, it set you up to make a mistake here. You look at this and you immediately want to. Oh, I see a force equation. I plug 16 in there, and if I did that, I'd get a value for the force. I know mass. I'll do acceleration. I'd be wrong, right? So we will do this. We'll go to the first part, and we will draw a free body diagram, right, of the car. Okay, what's going on? The car is moving in some direction. That's why he's not provided. We will set ourselves a direction, right? The car is moving, it's say, in this direction, okay? Which means reactive for resistive forces act in this direction, and that we will set as FR. If the car is moving in this direction at a constant velocity, that means there is a force which is coming from its engine, the power, and that is, I would say, this. You can call it FT for the traction force. I typically, or some people call it the driving force. I will call it the driving force, FD. And that's, so they have these two vectors. Constant velocity. So if the resistive force constantly applied and I have this, what am I trying to do here? Would this balance out? Well, if it's completely balanced, I'd have constant velocity. Okay. But clearly he doesn't say it's constant velocity. He says there is an acceleration component here, right? So we know here that FD is greater than FR. So it's overcoming resistance and it's driving forward. So that means there is a net force that's propelling this car ahead, right? So there is a net force. So our math would be the net force should be the driving force minus the resistive force. I think that would be more like it, right? If I did this as the net force and I want to do it as at velocity is equal to, and what velocity is he asking me to find that out? He just says 16. I want to say 16 meters per second. So at that time, the driving force doesn't change because we have power, right? But we know velocity and power, so we can calculate that, right? I would now write my F net as magnitude of this. Driving force is nothing but 20,000 divided by, let me go back, make sure I have it right, by 16. That's correct. Okay, minus, what's that force? That force is given by this equation, which is 120 plus 2 times 16 squared, which would give me, if I did the math, 16 squared is 256. I think I would have, what would be this net force roughly? Let me do the math. This should be about 1250, and that should be 632. Let's make sure I get this. I haven't made any mistakes here. I think that, yeah, 20. Yeah, that looks about right. Okay, which is equal to 618 newtons. Now I know at that velocity, this is the net force, which means that's 1. I also know that acceleration is equal to force by mass, which means at this force, 618 divided by a mass of 1,400, I should have, again, my math is not entirely, I did this really quickly, so the 0.44 meters per second square. That should be your equation. Right now, take one out. That's, if you've done that, I think the examiner has a fair idea of what you're trying to do. You've calculated the net force. You've said acceleration. Once you have the net force, you don't have to, write equation 1 and equation 2 and such. I think they'll be fairly comfortable to say, okay, you understand what's going on, and you should be fine. Now, you can get a little more specific by, calling this Fnet, right? And you can be more accurate, and they'll be fine with that too, right? Again, they're not asking for direction because they've given you speed, and therefore you don't need direction on acceleration either. So it's just fair enough for you to represent that. So that should cover the first part of this. Again, resist the temptation when you see a force value or you see power and say, oh, power is force times velocity. And if I just went in and plugged this as 16 and used this as the force of 1250 and applied that with M, I'd have a wrong answer. Or if I just did reactive force, it is understanding this force. Again, an A-level problem, testing your conceptual understanding of this, and of course your knowledge of what power is and how to apply them. Okay, so that's part 1 of this question. Part 2, if you look up there, the car now travels downhill on a straight road at an angle of 6 degrees to the horizontal. The driver wishes to maintain a constant speed of 20 meters per second. Show that the driver needs to brake. Again, let us go to a free body. Let us now do this. What's going on? We will now make a slightly exaggerated. The car is traveling downhill. Okay, so moment you have a car, you have mg there. It's traveling downhill. Direction of motion is there. Okay, what's going to happen here? Let's see. That's the direction of motion. There is resistive forces that are acting here. That doesn't change. Fr, he has not asked us to change that. We're going to keep that value as is. We will have here the force of the engine. I call it the driving force. Okay. We will also have, actually, maybe what I should do is just to make it simple for you. Given theta, this would be mg sine of 6 degrees. And we will have the driving force here, which is really coming from the power of that engine, and that varies with velocity. Now, if you were to maintain a speed of 20, so let's just see what happens to this case. If I was going to be at velocity of 20 for velocity equal to 20 meters per second, what is happening here? Well, very easily I can say driving force magnitude is equal to 20,000 divided by 20 is equal to 1,000 newtons. Gravitational force, F of gravity, is equal to mg sine of 6 degrees. Wow. These things make me a little bit uncomfortable. What is the sine of 6 degrees? Okay, you get a calculator and work this out. That should be 1400 times 9.8 times the sine of 6 degrees, 0.10453 is equal to 1434. I like to keep my decimals, so I will let that be. And given, and I would probably do it right there, given FR is, you're already told what FR is. Actually, no, it is a function, right? So I would probably do FR, magnitude of resistive force, and I'm going to put that into my 120 times 2 times 20 square. Did I get that right? I think so. So that's 400 times 2, 800, that's 920. So that's equal to 920 newtons. Okay, I got 1, 2, and 3 forces. Now, what is happening here? Clearly, the resistive force is in one direction, and you have, so let's just say there was no braking at that speed. If you were at that speed, net force equal to, and here's how I would do this. So I have the force of gravity helping me, I have the engine's power helping me, and then, so that would be 1434 plus 1000 minus 920, right? You can do the math here. Quite simply, it would be take it off, you get 80, and then 80 added to that gives you 1554. 1554 newtons in the direction of motion. Okay? Since this will accelerate the car, the driver must brake to maintain speed at 20 meters per second. That is how you would explain this. Again, this is more valuable to the examiner because they're not just saying, show me this calculation. And even if you didn't show this calculation, right? I did this to illustrate, but if you didn't show this calculation, they'd probably still be happy if you just said net force will tend to accelerate the car, and so the driver must brake to maintain speed at 20. So that's what the question is saying. Show that the driver, right? Sometimes he might ask you, explain why the driver must brake, right? And that's how you would do it. So it's a little more than just saying, hey, I've calculated a bunch of numbers. Here they're asking you to provide an explanation, right? Again, an A-level type problem. I haven't seen this come in on the AS or any other. In fact, most other high school curricula don't even get into this. So this is quite interesting that you know it, but you've got to state it. Okay, that's important. Let's go to the last part of this question. When the driver places the car in neutral so that it freewheels with no driving force and no braking force, find the max torque, similar to the previous problem. So again, we will come back to the part 3 of this problem and say, okay, so what's going on here? Same effect of this, right? So it's free, but there is no power of the engine. It's free. It's a neutral with freewheeling means there is no driving force here. So what is going on? The resistive force continues, right? And so here it's the same free body, but the only difference being because it's freewheel, driving force is 0, right? Therefore, what happens to your net force, or rather what's going on here, is you will have force due to gravity and resistance force, right? But at some velocity, he says, what's the maximum speed of the car? So that at some point, these forces cancel out. At max speed, acceleration equal to 0 implies net force equal to 0 implies, okay, magnitude of Fr is equal to mg sine of 6 degrees. Conceptually, right? And he wants you to find the velocity. We know that magnitude of Fr is a function of velocity. So I can write this as, and hopefully I'm still audible and this is clear, 120 plus 2 times velocity squared is equal to, didn't we do this math here somewhere? Cheating. 1434.13. So switch around, play with the numbers a little bit. What do I get? Velocity square is nothing but 1434.13 minus 120 divided by 2, and that gives me something to the tune of 657.07, which means velocity is equal, or the speed in this case, remember he's not asking, so is square root of that is 25.63 meters per second. maximum speed. Okay, hopefully I'm not casting a shadow on that. And that is quite similar to what we did in the previous problem where we just equated forces and solved for velocity, right? Again, the idea being understanding that driving force is disengaged. Again, you look at the problem, they expect a little more understanding of how these things work. And that's why that question said if he was in, if it was freewheeling, could have just said if there was no driving. But they say no, it's a neutral freewheels, and it makes it a little more juicier, rather expecting you to know more. But three parts, we saw that. First part, as long as the free body is there, we know the net force. From the net force, you've shown acceleration. They're quite happy. Second part, more valuable for you to work this out. Show them the calculation, but give them the explanation, right? If you didn't give them the explanation, they probably would not give you the marks for it. I don't remember how much. I think one of the Pearson textbooks has a problem like this, and I think this is 3 marks and 4 marks and 3 marks or something like that, or this is 5. They have a different point system, but this is typically how you resolve it. Watch for initial temptations when you come in here. If you have a tendency to start using this force or just resolve power, get the driving force and then try to find the acceleration. Don't do that. Always net the forces out. We net the forces out here, right? Same idea, and we net the forces there. So that is why one of the reasons why I wanted to make sure that I speak about problems after I talked about the equilibrium forces. But that ends the fourth problem I had. I'll probably have one or more videos beyond this, but I'm not going to use the board here to solve those problems. I'll probably use my computer and just use my writing tablet and solve some more problems just to give you an idea if you're getting stuck. But so far, I haven't gotten into elastic springs, but up until the idea of friction and the idea of motion, I think you're good. There are a lot of simpler problems that define textbook about simple collisions, transfer of momentum. But I thought our first problem there would be a good example of impulse and momentum, or the second problem we did from a vector perspective. All right. Once again, this is just insufficient. You need a lot more practice, and you should be able to solve these problems. I obviously went through a lot of explanations, but you should simply be able to put them down in this format without all those explanations. Put the diagram, go straight in and try and solve it. I tried to also show you work and force. How do you network and then figure out magnitude of force? I tried to show you, to use force to get work. You figure which one's better for you. But the idea is you should be able to do it rather quickly. You have a calculator on the exam, make sure you get your numbers done right. I have tended to skip some steps, but I think I've captured most of them fairly well. So keep those points in mind, and hopefully I'll get some more practice videos out. And yeah, good luck with practicing problems.